Hi, and welcome to this session where we'll take a look at the pole footing module in Structural Engineering Library. The first thing that we'll do is see how we can add a pole footing calculation to a project file. So I have a blank project file started. I'll click on Calculations in the Project Manager and then come up to the Add button. And in the Foundation group, I'll come down to the item called Pole Footing and give it a click. And now we see the pole footing embedded in soil module. So at this point we'll walk through each of the tabs in the input section as well as take a look at the results and see what the module offers. We'll start here on the General tab, and the first thing I'd like to point out is that the code references are provided here that will point you to the specific sections in IBC 2006 or in IBC 2009 where the referenced formula are included that are used in this module for the pole footing solution. If we come back over to the left, we have a general description field, so we can enter whatever is meaningful to us for this calculation. If we drop down below that description field, we have a pole footing shape selector. So notice that we can choose either to indicate a rectangular pole or a circular pole. When we enter a rectangular pole, we're entering the dimension, the side dimension of the pole, and it's the diameter when we use a circular pole. So I'll use circular, and I'm going to key in a 24-inch diameter and just register that value. The next thing that we have is a decision as to whether there is restraint provided to the pole at the ground surface or not. So we just make our decision with the appropriate checkbox. The important thing to note here is that as I make that change, you'll notice that there's an option over here to limit the allowable pressure, and that decision comes and goes depending upon which option I have here, as is consistent with the code. So what I will do for our purposes is I'll assume that there is no restraint at the ground surface so that it'll leave this additional option available for us to discuss. Continuing down on the left-hand side, we have another operational decision, which is to either let the module calculate the minimum required depth to satisfy the code criteria, or we can choose the option to solve for the lateral pressure at a particular depth, and then we can enter the actual pole footing embedment depth. So one might think of this as the decision between a brand new construction where you're able to solve for the required depth, and perhaps this could be thought of as checking an existing condition for a known embedment depth. So I'll leave it set to calculate a minimum depth for us. Now let's move up here and take a look at the allowable pressure limit option that we have. We're going to see the effect of this toggle once we provide some loads in the module, but there are two options. One of them is to limit the passive pressure only by the value that we enter here for the maximum lateral pressure limit. So that may be useful in situations where you already know that you have a code compliant maximum value specified and you don't feel the need to let the computer run through the process of comparing the embedment depth or the pressure at 1/3 of the embedment depth to the allowable pressure at 12 feet and so on. On the other hand, there's a convenient option here that says use the limit of 12 feet in accordance with IBC. And this is one that will make sure that the calculated or determined lateral pressure does not exceed the allowable lateral pressure determined at a depth of 1/3 of the embedment depth, but not to exceed a depth of 12 feet. So we'll play with those options a little bit and see how they affect the outcome. To start that, what we'll do is just choose the limit only by maximum passive pressure option. And then we'll come down and actually define our allowable passive pressure. So first what we have is the value of allowable lateral passive pressure in units of PSF per foot of depth. So I'll use that 250 PSF per foot depth. And then what I'm going to do is just make a quick comparison to the value that would result in at 12 feet, which would be 3000 PSF. So for comparison's sake, what I'll do is just set a maximum lateral pressure limit that's a little bit greater than that 3000 so that we can, again, observe the effects up here. So we'll see, or we'll set a value of 3500 PSF for that. And at this point, that completes the input for the general tab. So we will come back and revisit this information once we get through the other input here. But our next step would be to move on to the Applied Loads tab and specify the loads that are applied to the pole. Here on the Applied Loads tab, we have a few different options for the way that we can specify the loads that are applied to the pole. The overriding item of importance is that these should all be entered as unfactored loads, because coming up next will be a Load Combinations tab where we'll be able to specify all the different combinations that we want the program to run through. So notice that we have some major categories here. There are options to enter lateral concentrated loads, which would be of a specified magnitude and at a particular height above the ground surface. There's also an option to enter a lateral distributed load, which would be in units of kips per foot, and then it would require the definition of some extents, the distance from the ground surface to the bottom of the load and the distance from the ground surface to the top extent of the load in units of feet. And then we also have the ability to enter an axial load on the pole, which will be reported for us and compared or converted into an axial soil pressure for us as well. Now, there is a gap in the input here, and that area would allow for the entry of moments at the ground surface if back on the General tab we had chosen the option to say that the pole was restrained at ground surface. There we can see an applied moment input, and that's simply because the IBC formula that is used does not acknowledge a moment at the ground surface for the situation where there is no restraint at the ground surface. And so when the user indicates that there is no restraint, the Applied Loads tab hides that option to apply a concentrated moment at that ground surface elevation. So the user is free to enter any combination of loads that are displayed here. For our purposes, what I'd like to do is just enter a value of 110 kips, and I'm going to use a height above ground surface of 10 feet. And now what I'd like to do is just leave the rest of the loads blank for the time being, and I'd like to move over to the Load Combinations tab next. Here on the Load Combinations tab, we start off with a label that indicates the selected load combination set. Let's just assume that for our purposes we want to use the IBC 2009 load combination set. What I can do is come over to the button called Change Load Combination Set, give it a click, and from the pop-up menu I can choose the desired set. As soon as I do that, the name of the load combination set updates itself, and the factors in the table also update themselves to represent the load combinations as defined by the IBC 2009 set. Now, if any of these factors needed to be modified for a calculation-specific purpose, that's easily done. You can just toggle this little padlock icon here so that it appears unlocked, and then you can come into any of these cells and edit these values as you see fit. Rest assured that the changes that you make here in this table are not going to be retroactively reflected in the IBC 2009 load combination set in the load combination database, but instead they're only calculation specific. So they only apply to this one particular calculation, and the original load combination database with its factors remains intact and unchanged. I don't have any compelling reason to make any changes to this set of factors, so I'll just reset that lock toggle so that we can restore the original view. The other thing that's of interest, because we're looking at a soil-related design, we may receive information from the geotechnical engineer that indicates that for certain load combinations, perhaps those that include wind or seismic load, that we can allow some percentage of increase in the lateral soil bearing capacity. And so what we could do is come in using this soil increase column and select the load combinations that deserve that increase and then enter something appropriate like 1.33, for example, as an increase factor. Moving to the left, we see this column of check marks. That's just our method of indicating which load combinations we do want to have considered if they have a check, or indicating those that we don't want to have considered if we remove that check. And then with the run button at the head of the column, we have quick options like mark all, clear all, invert selections, and so on. The other thing I would point out here on the load combinations tab is that these load combination descriptions are taking their cues from the factors that are provided over here in the table. So if we were to come in, for instance, and unlock and make an edit to this particular load combination up here at the top, say 3 for a factor of H, notice that that description updates to reflect the factors and constituent load cases that we've included in the combination. So that's a convenient display of the actual factors that will be used in the analysis. The last thing that I'd point out here on the load combinations tab is the fact that the tab is labeled as service combinations, and that just helps us to remember that the analysis will be performed on the basis of service level load combinations. Okay, so that is a thorough look at all 3 input tabs. At this point, what I would like to do is just jump back to the General tab and make a quick comparison of some options that we saw here on the General tab. Before we move on to a thorough look at the bottom half of the screen and all of the results that are provided by the module, what I'd like to do now is just come back and revisit that comparison between these 2 options for establishing the allowable lateral pressure. Remember that we set an absolute lateral pressure limit of 3,500 psf. Remember that we sort of calibrated that value so that it was guaranteed to be larger than the magic number of 12 feet times 250, which would be 3,000 psf, and that for starters we chose this option to limit only by this maximum passive pressure option. So if we just take a peek down at the results, we can see that our solution came to a required embedment depth of some 45 plus feet, and that the actual lateral bearing pressure is, for all practical purposes, that 3,500 psf upper limit that we established. Now what I'd like to do is just reach back up and toggle to the option to use that 12-foot limit, because we know that using a limit of 12 feet to determine the allowable lateral passive pressure would limit the allowable value to 3,000 psf. And what we can see here is that now the program has automatically recalculated. It does obviously require a deeper embedment, but it also respects that 12 feet times 250 psf per foot value, which is the 3,000 psf, and it brings the design very efficiently right up to that allowable passive pressure limit. So this was just somewhat of an aside, but I just wanted to close that loop by revisiting this option once we had loads and load combinations defined, so that the meaning would be a little bit more clear here with these 2 options. The next thing that we'll do is take a more thorough look at the values that are provided down here on the Results subtab of the Calculations tab. Here on the Results tab, we start off by seeing the controlling values and an indication of the controlling load combination. Not terribly exciting because when we set up this problem, we only entered a couple of values for loads. But if we had entered a little bit more information for our applied loads, then we would obviously see a lot more information indicated down here in the Results tab. What we see is an indication of the actual applied lateral load and the moment at the ground surface. We see an indication as to whether we chose the option for restraint at ground level or not. In this case, we chose the option for no ground surface restraint. Then we see a report of the required embedment depth. I've just run the loads way up there so we could see a whole bunch of different load combinations. So we obviously have an extremely high embedment depth. And then an indication that it is controlled by the maximum passive pressure that was defined, as opposed to being limited by the IBC code limit if we had chosen this toggle. Then we can see the pressures reported at 1/3 of the embedment depth, so the actual and the allowable pressure. We can see the footing base area calculated for us. That's based on the fact that we specified a 24-inch diameter circle. And if I had specified any axial loads like this, then we would see a maximum axial soil pressure indicated as well. If we look at the table, we see a tabular display of all the load combinations that are run, and then forces at the ground surface in terms of a shear force and a moment. Then the calculation of the required embedment depth to satisfy those loads, a report of the pressure, the actual pressure, and the allowable pressure at 1/3 of the depth. And then we can see the vertical allowable pressure. So that's everything on the Results tab. The last thing that we'll take a look at is the Sketch tab, and this is just a graphical representation of the pole with the embedment shown. And if I bring things back into scale just a little bit by eliminating some of these loads, we can see something that's a little bit more meaningful. There we can see that we're representing the embedment of the pole in the footing, a little cross section indicating the footing diameter, the soil surface, and an indication that in our exercise there was no lateral restraint specified, and then the height of the pole so that we have that for reference to know where the applied loads occurred. So that's a look at everything that we have available to us on both of the Results tabs. The last thing that I'd like to mention is that once you get your design or your analysis set the way you want it, remember that you can come in and take a look at your design both in a preview format, print preview on the screen, or you can move directly to send to a PDF, or you can send it directly to your printer. So thanks very much. I hope it's been helpful. Take care and have a great day.